Here we have a circuit with two voltage sources, and we're asked to find the current flowing through the 50 ohm resistor. So that's this resistor here. So we need to find the current flowing through the resistor. Now there are different ways of doing this. Often when you see two voltage sources, you would think of using the superposition principle. So you would short circuit one of the voltage sources and calculate the current, and then you'd short circuit the other and calculate the current, and then you would add those two currents together. That's one way of doing it. Another might be to try to convert these voltage sources to current sources, and the reason is there's no way we can simplify these resistances. So these resistances are neither series nor parallel. But if we were to convert this into a current source, which would be a current source in parallel with the resistance, we would then have two parallel resistors. And the same with this. So the first thing to point out is this resistor here, this 25 ohm resistor, doesn't seem to be doing anything, because it doesn't matter what the current passing through this is. It doesn't change the potential difference between these 2 points, because that's guaranteed to be 40 volts. So we can effectively eliminate this, this resistance. So I can imagine that this resistor is somewhere here doing nothing. So this is my 25 ohms, and I can just scrap that as if it didn't even exist. Okay, so let's forget about this resistor because it doesn't affect the circuit at all. That's the first thing you would do when faced with a question like that. Okay, next, are there any easy simplifications here? So you see these three resistances, 1, 2, 3. They are clearly in series because they're each connected from one end. The same current passes through each of them. So we call these a series connection, and we can find the equivalent resistance there by adding them up. So 20 plus 10 plus 20. So that's 50 ohms. And as I said, this 25 ohm resistance, we can ignore that as if it doesn't exist. It's there in the background. So ignore that. So this has no effect on the circuit. Just consider it a separate circuit. Now, the next thing I would want to do is look at converting this voltage source into a current source, so that we would end up with a parallel or two parallel resistances. So to do that, the current in your current source would be the voltage or the EMF divided by the resistance. So in this case, it's 20 over 25, which is 4 over 5, or 0.8 volts. And you could do the same for this voltage source here, and you can say I equals 40 divided by 25, which is 1.6 volts. So now I'm going to eliminate this, convert this into a resistance, same resistance, in parallel with the current source of this value. I'm going to convert this and replace it with a current source of this value in parallel with the resistance of this, and I'm going to replace these three with a 50 ohm resistance. Okay, so that's my new circuit. So this 1.6 is that, this 0.8 is that, and the resistance values are unchanged, 25. So this is 25 ohms, and this is 25 ohms. And this is the series resistance, 50 ohms. Now I can combine parallel resistances. So these two I can now combine into one parallel resistance or equivalent resistance, and I can combine these two into one equivalent resistance. So that will give me equivalent of 1 over 20 plus 1 over 25. That should give me 100 over 9. And this just happens to be the same. So we have two lots of 100 over 9. I'm also going to combine these two. Okay, so bearing in mind that the current that they're after, they're looking for the current that passes through this 50 ohm resistor. And I don't know what direction it's passing, so I'm just going to assume an arbitrary direction, left to right. So this current, because these two are equal resistances, this current will be the same as that current. So whatever current enters here is going to be split into two equal halves. So if I find the current that's passing through this, so this is the equivalent resistance. So just to be clear, this is R equivalent 1 over 25 plus, 1 over 50, is it? Yeah, 1 over 50 plus 1 over 50. So that's 25. So here we have 25 ohms. I'll write it here, 25 ohms. So whatever current we end up finding here is going to be twice the current that would have passed through there, because the current splits equally between these two. Okay, so these two parallel resistances will combine into one, and then I can now convert my current source back to a voltage source. Now the reason I'm doing that is, so this is my voltage source and this is another voltage source. The reason I would do that is so that we now have series resistances, and you now have a simple circuit that you can either just apply Ohm's law or maybe a simple application of Kirchhoff's voltage law. So I'm going to quickly convert the sources again. So if you look at this current source, which was 1.6 amps, so the equivalent voltage source would have an EMF of the current times the resistance. So 1.6 times the equivalent resistance, which we said is 100 over 9. And that gives you 17.78 volts. So that's this voltage source. We'll do the same for this. So this resistance with this current, I think the current was 0.8 amps. So the EMF is 0.8 times 100 over 9. That gives you 8.89. So now we have a simple circuit with 2 voltage sources and 3 resistances in series. you can do a simple Kirchhoff's voltage law going around the loop, or you can simply add the EMFs and add the resistances because it's a series circuit and find the current. Now remember, we're assuming there's a single current, so it's a series circuit, so the current at every point is the same. And I've made the arbitrary decision that the current is going that way, so clockwise around the circuit, so from left to right through the 25 ohm resistance. That could be wrong, but it doesn't matter. That's my my initial choice. If it turns out to be negative, then we know that the current is going in the opposite direction. So if we tidy up a little, we now have two voltage sources, one that would drive current this way and the other that would drive current this way. So when adding these two, this would be positive and this would be negative because they're in opposite direction. If you were to do a Kirchhoff's voltage law, it would be apparent. So if we find the total resistance, it's simply the sum of the EMFs divided by the equivalent resistance. So it would be 8.89 minus 17.78 divided by the sum of these three resistances. And remember, each of these is 100 over 9. So you've got 100 over 9 and 25 and 100 over 9. So if you do that calculation, 8.89 minus 17.78 over 200 over 9 plus 25. That gives you 188.3 milliamps. So I total equals 188.3, and it's negative. The reason it's negative, well, the reason I found it to be negative is because it's this take away this. But now we know that it's negative. That tells us that our assumed direction is incorrect and the current is actually going in the opposite direction. The other thing we need to remember is the question wasn't asking about this current. The question said, what's the current passing through the 50 ohm resistor? So the current here isn't the same as the current passing through this equivalent resistance. So remember we said the current splits in two. So whatever we find here, or whatever we find here, we need to divide it by 2 to find the current passing through the 50 ohm resistor. So we can say the current passing through the 50 ohm resistor is the total current divided by 2. So if I were to divide that answer by 2, I would get negative 94.1 milliamp. Okay, now to deal with the negative sign, so what we have is a 50 ohm resistor and the current going in this direction is negative 94. So we can conclude that the actual current passing through the resistor is 94.1 milliamps in the direction opposite to our initial assumption. So in this case, it will be right to left. So this would be your final answer.